What if everything we thought we knew about the universe was just the tip of the cosmic iceberg? Picture this, a vast, ever-changing cosmos where the rules of physics twist in ways we never anticipated, where planets wander alone through the darkness, and signals from the depths of space hint at mysteries we can barely comprehend. This isn't science fiction, this is reality, and every single day, astronomers and scientists uncover something new that flips the script on what we thought was possible. Welcome to a journey through 30 of the most unexpected cosmic discoveries that keep rewriting the rulebook of our universe. Think about the last time you looked up at the night sky. It probably felt familiar, maybe even predictable, the same constellations, the same steady glow of distant stars. But behind that serene facade, the universe is anything but calm. It's a place of chaos and wonder, where black holes collide, invisible forces shape galaxies, and entire planets defy the laws of gravity. Some of these discoveries are so bizarre they sound like they're straight out of a fantasy novel. Yet they're real, documented, and waiting to blow your mind. This isn't just a list of cool space facts. It's an exploration of how these revelations force us to rethink our place in the cosmos. What if the universe is far stranger, far more unpredictable than we ever dreamed? From enigmatic radio bursts repeating like cosmic Morse code to rogue planets drifting untethered from any star, each discovery we'll uncover today challenges the very foundations of astronomy. And the best part, this is only the beginning. Every new telescope, every mission into the unknown, brings us closer to uncovering secrets that could change everything. So buckle up, because by the end of this journey, you'll never look at the night sky the same way again. Imagine a signal so powerful it outshines entire galaxies, but only for the blink of an eye. That's the enigma of fast radio bursts, cosmic flashes so intense they release more energy in milliseconds than our sun does in 80 years. First detected in 2007, these bursts arrive from billions of light years away, vanishing almost as quickly as they appear. At first, astronomers wondered if they were glitches, some artifact of Earth's technology interfering with their instruments. But as more were recorded, the truth became undeniable. These were real, and they were coming from the deepest corners of space. What makes them even stranger is their unpredictability. Most fast radio bursts fire once and never repeat, like cosmic firecrackers echoing through the void. But a handful defy expectations, pulsing at irregular intervals with no discernible pattern. One famous repeater, known as FRB 121102, has been flaring sporadically since its discovery, taunting scientists with its cryptic rhythm. The randomness fuels wild theories. Could these be alien beacons, deliberate signals from civilizations far beyond our own? While that possibility sparks the imagination, the leading explanation is far more exotic, yet no less fascinating. The prime suspect, magnetars, the universe's ultimate cosmic powerhouses. These ultra-dense, spinning neutron stars are wrapped in magnetic fields so strong they could strip the data from a credit card halfway across the galaxy. When their crusts crack under unimaginable pressure, they might unleash these explosive radio bursts. In 2020, astronomers caught a smoking gun. A magnetar in our own galaxy erupted with a burst strikingly similar to those from deep space. It was the first tangible clue linking these bizarre signals to a known phenomenon. Yet not all fast radio bursts fit this mold. Some are too energetic, too far away, or too repetitive to be explained so easily. This cosmic detective story forces us to confront how little we truly understand about energy in the universe. If something so fleeting can outshine galaxies, what else is lurking in the darkness, unseen and unexplained. Every new fast radio burst detected adds another piece to the puzzle, but the full picture remains maddeningly out of reach. And that's what makes them so thrilling. They're a reminder that the cosmos still holds secrets we've only begun to uncover. Just when we thought we had the universe figured out, it threw us another curveball, one so massive it rewrote the textbooks overnight. In the late 1990s, two teams of astronomers were studying distant supernova, expecting to confirm what everyone believed, that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down. Instead, they found the opposite. The universe wasn't just growing, it was accelerating, as if some invisible hand was pressing harder on the cosmic gas pedal with each passing moment. This baffling force earned a name as mysterious as its behavior: dark energy. Think of it as the universe's ultimate enigma, making up roughly 68% of everything that exists, yet remaining completely invisible to our telescopes. Its discovery didn't just surprise scientists, it upended centuries of assumptions about gravity, space, and the fate of the cosmos. Einstein himself once proposed a similar concept, calling it the cosmological constant, but even he later dismissed it as his greatest blunder. Turns out he might have been onto something all along. The implications are staggering. If dark energy keeps pushing galaxies apart faster and faster, the universe could face a chilling future, one where distant galaxies vanish from view entirely, their light stretched too far to ever reach us. It's a scenario called the Big Freeze, where space itself becomes so vast and empty that future civilizations might look up at a night sky devoid of stars, with no clue that other galaxies ever existed. But here's the twist: we still don't know if dark energy is constant or if its strength changes over time. Some theories suggest it could grow stronger, eventually tearing apart everything down to atoms in a catastrophic Big Rip. What makes dark energy so maddening is that it defies detection. Unlike dark matter, which tugs on stars and galaxies with its gravity, dark energy seems to be a property of space itself, a repulsive force woven into the fabric of reality. Is it a new kind of energy field, a flaw in Einstein's equations, or something even stranger that we haven't imagined yet? Every attempt to pin it down only deepens the mystery. Even our most advanced telescopes and particle colliders have yet to crack its code. This isn't just a puzzle for astrophysicists, it's a humbling reminder of how much we still don't understand. Dark energy forces us to confront the possibility that our current laws of physics might be incomplete, that there are realms of reality operating beyond our grasp. And yet, that's what makes cosmology so thrilling. Each unanswered question is an invitation to explore further, to push the boundaries of human knowledge. Because if history has taught us anything, it's that the universe always has another surprise waiting just beyond the edge of our understanding. There's an invisible tug of war happening right now, and you're part of it. Picture the Milky Way, our cosmic home, hurtling through space at over 2 million kilometers per hour. But here's the catch: we're not just drifting aimlessly. Something out there, something colossal, is pulling us and thousands of other galaxies toward it with a gravitational grip so strong it defies logic. Astronomers call it the Great Attractor, and its mystery is as vast as its influence. For decades, this enigmatic region remained hidden in plain sight, obscured by the thick dust and stars of our own galaxy's disk. Even now, peering through that cosmic veil is like trying to spot a lighthouse through a sandstorm. But the clues are undeniable. When scientists mapped the motion of galaxies across the universe, they noticed something bizarre. Everything in our corner of space, including the entire local group of galaxies, is streaming toward a single point in the constellation Centaurus. It's as if the universe has a hidden current and we're all caught in its flow. So what exactly is this unseen behemoth? The leading theory points to an unimaginably dense cluster of galaxies, a gravitational titan with the mass of tens of thousands of Milky Ways. But here's where things get weird. Even when accounting for every visible galaxy in that region, the math doesn't add up. The Great Attractor's pull is far stronger than what visible matter alone can explain. That's led some scientists to propose an even wilder possibility. What if this isn't just a cluster, but a junction point where multiple superclusters converge, woven together by vast filaments of dark matter? The implications are staggering. If true, it means the Great Attractor isn't just a destination, it's a signpost pointing to an even larger cosmic structure. Recent observations hint at an enormous overdensity of galaxies nicknamed the Laniakea supercluster, a web-like sprawl spanning 500 million light-years with the Great Attractor at its heart. This would make our Milky Way nothing more than a speck on the edge of a colossal celestial watershed, drifting toward its gravity well like a leaf caught in a river's current. Yet for all we've pieced together, the Great Attractor remains one of cosmology's most humbling puzzles. It challenges our understanding of how matter is distributed in the universe and forces us to confront how little we truly see. Nearly 95% of the cosmos is invisible dark matter and dark energy, and this mysterious region might be our best clue to mapping that hidden landscape. Every new telescope, from radio arrays piercing through galactic dust to next-generation space observatories, brings us closer to unraveling its secrets. What's most thrilling is the possibility that we've only scratched the surface. Could there be even larger structures lurking beyond our current maps, their gravitational fingers subtly steering the motion of galaxies? The Great Attractor isn't just pulling us through space, it's pulling our curiosity toward ever deeper questions about the universe's hidden architecture. And that's the beauty of cosmic discovery. Each answer reveals a new layer of mystery, reminding us that the universe is always more complex, more wondrous than we ever imagined. Stars are supposed to be predictable, steady beacons of light governed by the reliable rhythms of physics. But then there's Tabby's star, a cosmic rebel that plays by its own rules. Officially catalogued as KIC 8462852, this unassuming star in the constellation Cygnus has become one of astronomy's greatest head-scratchers. Unlike ordinary stars, which dim in predictable, gentle patterns when planets pass in front of them, Tabby's star plunges into darkness erratically, sometimes by as much as 22%. That's like someone flipping a celestial dimmer switch, leaving scientists scrambling for explanations. When the Kepler Space Telescope first spotted these bizarre dips in 2015, the data seemed almost too strange to believe. Planets, even giant ones, typically block less than 1% of a star's light. But here was a star whose brightness nosedived in jagged, asymmetrical patterns, as if something enormous and irregular, something utterly unlike a planet, was drifting across its face. Early theories ranged from the plausible to the downright fantastical. Could it be a swarm of comets, thousands strong, trailing enough dust to blot out the star's light? Or was this the signature of something even more extraordinary, an alien megastructure like a Dyson sphere designed to harness a star's energy? The alien hypothesis, while thrilling, faced immediate skepticism. After all, extraordinary claims require extraordinary evidence. But what made Tabby's star so compelling was that even the more conservative explanations fell short. Dust seemed the most likely culprit, yet the star's longer-term behavior added another layer of mystery. Historical data revealed that over the past century, Tabby's star had faded by an astonishing 14%, a decline completely unprecedented for a star of its type. Dust clouds might explain short-term dimming, but such a dramatic, century-long trend defied easy explanation. Then came another twist. In 2017, the star's unpredictable dimming episodes returned, and this time astronomers were ready. Telescopes around the world trained their sights on it, capturing the event in unprecedented detail. The data revealed something critical. The star dimmed more in blue light than in red, a telltale sign of fine dust particles scattering shorter wavelengths. This was the smoking gun pointing to dust as the primary culprit, not solid objects like megastructures, but something far more mundane. Yet even with this answer, the puzzle isn't fully solved. Where is all this dust coming from? Why does it behave so erratically? And what's responsible for the star's century-long fading? Some theories suggest a recent planetary collision, creating a chaotic debris field. Others propose a natural but poorly understood stellar phenomenon, like magnetic activity gone haywire. Whatever the truth, Tabby's star stands as a reminder that the universe loves to defy our expectations. Just when we think we've got stars figured out, one comes along and throws the rulebook out the window. What makes this discovery so exhilarating isn't just the mystery itself, it's the way it forces us to question our assumptions. Every time we observe something that doesn't fit the mold, it's an opportunity to learn, to adapt, and to expand our understanding of the cosmos. Tabby's star may not be surrounded by alien megastructures, but in a way, it's done something even more remarkable. It's shown us that even the most familiar objects in the universe can still surprise us. And that's a lesson as valuable as any discovery. Dark matter is supposed to be the universe's invisible scaffolding, the hidden framework that holds galaxies together. For decades, every observation confirmed this rule. Where there's a galaxy, there's dark matter. That is, until astronomers stumbled upon NGC 1052DF2, a galaxy that defies all expectations. This cosmic oddball, floating in the constellation Cetus, appears to have almost no dark matter at all. At first, scientists assumed their measurements had to be wrong. How could a galaxy exist without the very thing thought to be essential for its existence? The discovery sent shockwaves through astrophysics because it challenges one of our most fundamental assumptions. Dark matter isn't just some minor ingredient. It's thought to make up about 85% of all matter in the universe. Its gravitational pull is what keeps galaxies from flying apart as they spin. Without it, stars on the outer edges of galaxies should be flung into the void like riders on a broken merry-go-round. Yet NGC 1052DF2 spins calmly, its stars moving at speeds that shouldn't be possible without dark matter's anchoring grip. It's like finding a skyscraper standing tall with no foundation. So how did this galaxy break the rules? One theory suggests it might be the result of a cosmic accident. Picture two galaxies colliding, a violent event that could strip away dark matter, leaving behind a cluster of stars drifting alone. Another idea posits that NGC 1052DF2 formed in an unusual environment, perhaps near a massive galaxy whose gravitational tides siphoned away its dark matter. But here's the catch. Even these explanations struggle to account for just how little dark matter this galaxy seems to have. If it were merely depleted, we'd expect traces to remain. Instead, the measurements suggest it's almost entirely absent. The implications are staggering. If galaxies can form without dark matter, then our understanding of how structures emerge in the universe might need a complete overhaul. It's like discovering a tree that grows without roots. Everything we thought we knew about galaxy formation suddenly has a glaring exception. Some researchers even speculate that NGC 1052DF2 could be part of an entirely new class of galaxies, ones that follow a different set of cosmic rules. But the mystery deepens. Subsequent observations revealed another oddball, NGC 1052DF4, which also appears to lack dark matter. This can't be a fluke. There's a pattern here, one that suggests our models are missing something crucial. Could dark matter interact in ways we haven't anticipated? Or is there an alternative explanation for how galaxies hold themselves together? Every new observation chips away at the old certainties, reminding us that the universe is far more inventive than our theories. What makes this discovery so exhilarating isn't just the puzzle itself, it's the way it forces us to rethink the basics. For years, dark matter seemed non-negotiable, a cornerstone of cosmology. Now, we're faced with the tantalizing possibility that the universe has more than one way to build a galaxy. Whether NGC 1052DF2 is a cosmic outlier or a sign of something deeper, one thing's clear: the rulebook of the cosmos is still being written, and every page holds a new surprise. There's a crack in the foundation of cosmology, and it's growing wider every year. The Hubble constant, the number that tells us how fast the universe is expanding, should be one of the most straightforward figures in astrophysics. Yet when scientists measure it using different methods, they keep getting two distinct answers that refuse to match up. This stubborn discrepancy, known as the Hubble tension, isn't just a minor accounting error. It's a glaring signal that somewhere in our understanding of the cosmos, something fundamental is missing. One approach to calculating the Hubble constant relies on the cosmic microwave background, the faint afterglow of the Big Bang. By studying subtle ripples in this ancient light, scientists can extrapolate how quickly the universe should be expanding today. Their answer: roughly 67 kilometers per second per megaparsec. But when astronomers measure nearby supernova or pulsating stars called Cepheids, objects whose brightness reveals their distance, the expansion rate jumps to about 73. That 6-kilometer gap might sound small, but in the precise world of cosmology, it's a chasm. Imagine stepping on two different scales and getting weights that differ by 20 pounds. You'd assume one was broken, yet in this case both methods are meticulously vetted, peer-reviewed, and repeatedly confirmed. The scales aren't broken. The problem runs deeper. What makes the Hubble tension so unsettling is that it challenges the standard model of cosmology, our best blueprint for how the universe works. This model, built on decades of observations and theoretical work, has predicted countless cosmic phenomena with astonishing accuracy. But now, faced with irreconcilable measurements, scientists are forced to ask, is the model incomplete? Some propose exotic solutions, like undiscovered particles that subtly alter the universe's expansion. Others suggest modifications to Einstein's theory of gravity itself, tweaking the rules that govern how matter and energy shape spacetime. Then there's the wildcard possibility that we're seeing evidence of a previously unknown force or field, something entirely outside our current physics. The stakes couldn't be higher. If the Hubble tension points to new physics, it would rank among the most profound discoveries of the century, rewriting textbooks and reshaping our view of reality. But even if the explanation turns out to be more mundane, a hidden systematic error or overlooked variable, the process of solving this puzzle is already driving innovation. New telescopes like the James Webb Space Telescope are refining distance measurements with unprecedented precision. Next-generation observatories aim to map the universe's expansion in 3 dimensions, searching for clues in the large-scale structure of galaxies. What's fascinating is how this conflict mirrors the scientific process itself. Discrepancies aren't failures, they're guideposts pointing toward gaps in our knowledge. The Hubble tension doesn't mean cosmology is broken. It means cosmology is alive, a field where even the most established ideas must adapt when faced with new evidence. And that's the beauty of this moment. Whether the answer lies in dark energy's secrets, gravity's quirks, or something no one has yet imagined, one thing is certain. The universe still has surprises up its sleeve, and unraveling them will take us closer to truths we can't yet fathom. In October 2017, astronomers spotted something unprecedented, a visitor from another star system streaking through our solar system at breakneck speed. Dubbed Oumuamua, Hawaiian for scout, this cosmic interloper was the first object ever detected that originated beyond our sun's influence. At first glance, it seemed ordinary, a small, fast-moving speck of light. But as telescopes tracked its trajectory, it became clear this was no typical space rock. Its peculiarities began piling up like clues in a cosmic mystery novel. For starters, its shape defied all expectations. Most asteroids and comets are roughly spherical or lumpy, but Oumuamua was elongated, stretching perhaps 10 times longer than it was wide, like a celestial cigar tumbling through the void. Then came the real shocker, its movement. As it raced away from the sun, it didn't just coast on gravity's pull. Instead, it accelerated slightly, as if propelled by an unseen force. Comets often behave this way when sunlight vaporizes their icy surfaces, creating a gaseous tail that acts like a natural thruster. But Oumuamua showed no visible coma or tail, no cloud of dust or gas that could explain its speed boost. The scientific community erupted with theories. Some proposed it was a rare type of dark comet, a body with hidden reservoirs of ice that sublimated just enough to nudge it forward without producing a detectable trail. Others suggested more exotic origins, perhaps a shard of a shattered planet, ejected from a distant star system eons ago. Then came the most provocative idea: could Oumuamua be artificial? The possibility, though slim, couldn't be entirely dismissed. Its unusual shape and motion led a few researchers to speculate about solar sails or derelict alien technology, though most astronomers emphasized natural explanations were far more likely. What makes Oumuamua so fascinating isn't just its oddities, it's the door it kicked open in planetary science. Before its arrival, models suggested interstellar visitors should be rare, maybe one passing through every few decades. Yet within 2 years, a second object, Comet Borisov, was spotted. Suddenly, it seemed the cosmos might be teeming with transient debris, each carrying secrets from alien star systems. Oumuamua's brief appearance forced us to confront how little we know about objects born around other suns. Are they all this strange, or was our first guest an outlier? The debate over Oumuamua's true nature still simmers, a testament to how one unassuming object can upend assumptions. It's a reminder that the universe doesn't play by our expectations sometimes. It sends a tumbling, speeding enigma to shake up the textbooks. And with next-generation telescopes like the Vera Rubin Observatory set to scan the skies, we're bound to find more of these interstellar nomads. Each one will be a time capsule, a fragment of another world's history, and perhaps, just perhaps, a messenger with stories we've yet to imagine. Deep within the Milky Way's bustling center, something erupted with unimaginable force not once but twice. The evidence: 2 colossal orbs of energy, each towering 25,000 light-years above and below the galactic plane, like ghostly hourglasses framing our entire galaxy. These are the Fermi Bubbles, first spotted in 2010 by NASA, a Fermi gamma-ray space telescope, and they're anything but ordinary. Glowing with high-energy gamma rays, these structures aren't just massive, they're relics of a cataclysm so powerful it reshaped our galactic neighborhood, leaving behind a mystery we're still unraveling. What makes these bubbles so baffling is their sheer scale. If you could see them with the naked eye, they'd span half the night sky, dwarfing every constellation. Yet their origin story remains a cosmic whodunit. The prime suspect, our galaxy's supermassive black hole, Sagittarius, a star, Normally, this behemoth is relatively quiet, but astronomers suspect it wasn't always so well behaved. Around 4 million years ago, it might have gone on a feeding frenzy, swallowing a gargantuan clump of gas and stars. The resulting explosion would have been epic, a jet of energy erupting from the black hole's poles at near light speed, punching through interstellar gas and carving out the bubbles we see today. But here's the twist: not everyone's convinced. Some researchers argue the Fermi Bubbles could be the aftermath of a galactic collision, a long-ago encounter with a smaller galaxy that sent shockwaves rippling through the Milky Way. Others propose an even wilder idea, that they're the accumulated bursts of thousands of exploding stars, a chain reaction of supernova that lit up the galactic center like a string of firecrackers. The truth might lie somewhere in between, a combination of events that left these faint, shimmering fingerprints in the gamma-ray sky. What's especially intriguing is how the bubbles force us to rethink our galaxy's personality. We often picture the Milky Way as a serene, twirling disk of stars, but these structures reveal a far more tempestuous past. They're proof that even seemingly stable galaxies have explosive moods, capable of violence on scales we're only beginning to comprehend. And they're not alone. Similar bubbles have been spotted in other galaxies, hinting that this might be a universal phase galaxies go through, like cosmic growing pains. The deeper we look, the more questions arise. Why do the bubbles have such sharp edges, as if someone traced them with a cosmic stencil? What's generating the high-energy particles inside them, and could such an eruption happen again? With every new observation, from radio waves to X-rays, we're piecing together a story of chaos and rebirth, one that reminds us the Milky Way isn't just a static backdrop, it's a dynamic, ever-changing entity with scars to prove it. Perhaps the most thrilling part is what the Fermi Bubbles represent, a glimpse into the hidden forces shaping galaxies. They're not just fossils of the past, they're active laboratories where particles accelerate to energies that dwarf anything we could create on Earth. Studying them might unlock secrets about dark matter, cosmic rays, and even the elusive nature of black holes themselves. So while their origins remain shrouded in mystery, one thing's certain: the Fermi Bubbles are more than just a cosmic oddity. They're a window into the Milky Way's wilder side, a side we're only just beginning to explore. LTT 9779b shouldn't be here. This Neptune-sized planet orbits its sun-kissed star so closely that a single year lasts just 19 hours, a blistering dance where temperatures soar to nearly 2,000 degrees Celsius. At that distance, most planets like it would have been stripped bare eons ago, their atmospheres boiled away by relentless stellar radiation. Yet against all odds, LTT 9779b persists, wrapped in a shimmering cloak of gas that defies every expectation. It's the cosmic equivalent of finding an ice cube surviving in a furnace, and its very existence is forcing astronomers to rewrite the rules of planetary survival. What makes this world so baffling isn't just its resilience, it's the sheer improbability of its size. Planets this close to their stars are usually either scorched, rocky husks like Mercury, or bloated gas giants too massive to evaporate. LTT 9779b sits awkwardly in between, a hot Neptune occupying what scientists once called the hot desert, a region where mid-sized planets simply shouldn't exist. Theory predicted that stars would rip away the fluffy atmospheres of planets like this within a few million years, but here it is, billions of years later, still clinging to its gaseous envelope. The question isn't just how it survived, it's how anything like it could ever form in the first place. One clue might lie in its bizarre reflective properties. Observations reveal that LTT 9779b's atmosphere is eerily shiny, bouncing back 80% of the light that hits it, making it one of the most mirror-like planets ever discovered. Some scientists speculate this metallic sheen could come from clouds laden with titanium or silicate, a natural sunscreen deflecting just enough stellar fury to preserve the planet's atmosphere. Others propose it might have started life as a much larger gas giant, its outer layers vaporized until only a dense, reflective core remained. But even these theories struggle to explain why similar planets haven't been found elsewhere in the galaxy's hot deserts. Then there's the wild-card possibility. What if this planet didn't form here at all? Some models suggest LTT 9779b could be a migrant, born farther out in its system before spiraling inward. During this journey, it might have developed an ultra-dense atmosphere, one too stubborn to evaporate even under its star's withering glare. It's a cosmic Hail Mary, but until we find more of these oddballs, every explanation remains on the table. The implications ripple far beyond this single world. If hot Neptunes can thrive in places we thought impossible, what else have we gotten wrong about planetary evolution? Could there be entire classes of planets lurking in the universe's harsh environments, invisible to our assumptions? LTT 9779b isn't just a curiosity, it's a challenge, a reminder that the universe delights in serving up exceptions to every rule we try to impose. And with next-generation telescopes honing in on exoplanet atmospheres, this rebellious world might soon have company, teaching us just how creative and stubborn cosmic evolution can be. Picture the universe not as a random scattering of galaxies, but as an intricate tapestry, one woven with threads so faint they're nearly invisible, yet so powerful they dictate the fate of everything we see. This is the cosmic web, a vast network of dark matter filaments stretching across billions of light years, connecting galaxies like beads on an invisible string. For decades, it existed only in theory, a ghostly framework inferred from the way galaxies clustered together. But now, thanks to cutting-edge telescopes and ingenious mapping techniques, we're finally seeing these dark threads in stunning detail, and what they reveal is rewriting our understanding of cosmic architecture. The breakthrough came when astronomers realized they could use distant quasars' extremely bright galactic cores as cosmic flashlights. As the light from these quasars travels toward Earth, it passes through the faint gas clinging to dark matter filaments. Like a spider's web glistening with morning dew, these filaments leave subtle fingerprints in the quasar light, allowing scientists to trace their otherwise invisible forms. The resulting maps are breathtaking, a labyrinth of dark matter threads, some stretching hundreds of millions of light years, with galaxies perched at their intersections like knots in a net. It's proof that the universe isn't just expanding, it's structured, organized by an unseen hand. What's most astonishing is how much weight these delicate-seeming threads bear. Dark matter makes up about 85% of the universe's mass, and its gravitational pull is what sculpts the cosmic web. Without it, galaxies would drift apart, unmoored and disconnected. But thanks to this hidden scaffolding, they're drawn together along these filaments, funneled into dense clusters or stretched into sprawling walls. The cosmic web isn't just a backdrop, it's the universe's circulatory system, guiding the flow of matter over eons. Yet the more we learn, the more mysteries emerge. Why do some filaments appear denser than others? How do they influence the birth and death of galaxies? And what happens in the voids between them, those vast, empty regions where the web's grip is weakest? Some theories suggest these voids might hold clues to dark energy's influence, acting as cosmic laboratories where expansion outmuscles gravity. Others speculate that the web itself could be vibrating with low-frequency waves, echoes of the universe's earliest moments. This discovery does more than fill in a missing piece of the cosmic puzzle. It forces us to confront how little we truly see. The cosmic web's dark threads are a humbling reminder that the visible universe, the stars and galaxies we admire through telescopes, is just the glittering fringe of something far grander and more mysterious. And as our maps grow sharper, revealing finer strands and subtler connections, one thing becomes clear: the universe isn't just expanding randomly. It's growing according to a hidden blueprint, one we're only beginning to decipher. Most of the universe is crowded with galaxies clustered together in bustling superclusters or strung along vast cosmic filaments. But then there's the Boötes Void, a staggering cosmic desert so empty it feels like the universe forgot to fill it in. Spanning 330 million light-years, this void is a gaping hole in the cosmic web, a region where galaxies are almost entirely absent. If the Milky Way sat at its center, we wouldn't have known other galaxies existed until the 1960s. That's how sparse it is, a yawning abyss that defies everything we thought we knew about how matter arranges itself in space. The mystery begins with the numbers. On average, a region this size should contain at least 2,000 galaxies. The Boötes Void holds just 60, scattered like lost travelers in an endless wasteland. At first, astronomers assumed their telescopes simply weren't sensitive enough to spot fainter galaxies lurking in the darkness. But deeper surveys confirmed the unsettling truth: this void is real and its emptiness is profound. What could have carved out such a void? One leading theory suggests it's the result of smaller voids merging over billions of years, like soap bubbles coalescing into one enormous cavity. Another, more radical idea proposes that the void might be a fingerprint of exotic physics, a region where dark energy's repulsive force worked overtime, pushing matter away with unusual intensity. Yet even these explanations leave gaps. If smaller voids merged, why didn't filaments of galaxies survive the process? And if dark energy played a role, why don't we see other voids this extreme? Some researchers speculate the Boötes Void could be a statistical fluke, a 1 in a trillion underdensity in an otherwise balanced universe. Others wonder if it's evidence of something stranger, like a collision with a parallel universe or a defect in the fabric of spacetime itself. The wildest theories remain on the fringe, but the void's sheer scale forces us to consider possibilities we might otherwise dismiss. What makes the Boötes Void so captivating isn't just its emptiness, it's what that emptiness reveals about the universe's structure. Voids aren't anomalies, they're a natural part of the cosmic web, the flip side of galaxy-rich clusters. But the Boötes Void is an outlier, a place where the rules seem to bend. Studying it could help us understand the limits of cosmic inflation, the era when the universe expanded faster than light in its first fleeting moments. Perhaps this void is a relic of that explosive birth, a pocket where inflation stretched spacetime just a little further, leaving behind a vacuum unlike any other. The more we probe this cosmic oddity, the more questions arise. Are there galaxies hidden in its depths, too faint for our telescopes to see? Could its gravitational pull be subtly distorting the motion of nearby galaxies, leaving clues about the nature of dark matter? And if voids like this are possible, what other extreme structures might lurk in the universe's uncharted corners? The Boötes Void doesn't just challenge our models, it invites us to rethink the boundaries of what's possible. In a cosmos teeming with galaxies, sometimes the most profound mysteries lie in the places where almost nothing exists at all. 55 Cancri sounds like something out of a science fiction novel, a planet where the very ground beneath your feet might glitter with unimaginable riches. Orbiting a star just 40 light-years away, this super-Earth is one of the most exotic worlds ever discovered, and for good reason. under crushing pressures and scorching temperatures, its carbon-rich composition has likely crystallized into something extraordinary, a vast planetary diamond. That's right, a world where diamonds aren't rare gems but the bedrock of the landscape itself. What makes this planet so baffling isn't just its hypothetical sparkle, it's the sheer improbability of its existence. Most rocky planets, like Earth, form from silicon and oxygen-rich materials with carbon playing a minor role. But 55 Cancri e seems to have bucked the trend, emerging from a protoplanetary disk brimming with carbon. Imagine a cosmic forge where graphite, subjected to temperatures over 2,000 degrees Celsius and pressures millions of times greater than Earth's surface, is compressed into diamond. That's the daily reality for this bizarre world, where the very laws of chemistry twist into something unrecognizable, yet the surprises don't stop there. 55 Cancri e orbits so close to its star that a single year lasts just 18 hours, locking one hemisphere in perpetual daylight while the other broils in endless night. Surface temperatures on the day side could melt iron, creating lakes of lava that shimmer beneath a sky thick with carbon-rich vapors. Some models even suggest the planet might rain diamonds, with carbon atoms in the upper atmosphere bonding under extreme heat and pressure before crystallizing and falling like gemstone hail. It's a world where the line between geology and alchemy blurs beyond recognition. The discovery of 55 Cancri e didn't just add another planet to the catalogue, it shattered assumptions about planetary diversity. Before its detection, no one seriously considered that diamond planets could exist, let alone thrive in such hostile environments. Now, astronomers wonder how many more of these glittering oddballs might be hiding in the cosmos. Could there be entire systems where carbon worlds outnumber rocky ones? And what does that mean for our understanding of planet formation? If a star's composition leans carbon-heavy, does it inevitably spawn diamonds instead of Earth-like worlds? Perhaps the most tantalizing question of all is what 55 Cancri e teaches us about the universe's creativity. We often assume that planets must follow familiar templates, rocky, gaseous, or icy, but this diamond super-Earth proves the cosmos has a far richer imagination. It's a reminder that the universe doesn't just play by the rules we've written, it invents new ones on the fly, and with every new discovery, we're left marveling at just how strange, how wondrous, and how utterly unexpected the cosmic story can be. Black holes aren't supposed to break the rules, at least not like this. When the LIGO and Virgo gravitational wave detectors picked up the signal from GW 190521 in 2019, astronomers knew they had something extraordinary on their hands. The ripple in spacetime revealed a collision between two black holes, but not just any black holes. These were cosmic heavyweights, each roughly 85 times the mass of our Sun, merging to create an even more monstrous black hole of 142 solar masses. On the surface, that might not sound unusual except for one glaring problem. Black holes this massive shouldn't exist. According to everything we know about stellar evolution, stars between 65 and 130 solar masses don't collapse into black holes at all. Instead, they undergo something called pair instability supernova, a runaway thermonuclear explosion so violent it obliterates the star completely, leaving nothing behind. So how did GW 190521's black holes bypass this cosmic self-destruct mechanism? One possibility is that they weren't born from single collapsing stars, but formed through successive mergers in densely packed star clusters, like cosmic Russian dolls stacking up over eons. Another, even more radical idea suggests they might have emerged from direct collapse, skipping the star phase entirely, when massive clouds of primordial gas collapsed under their own gravity in the early universe. The implications are staggering. If black holes can form through these alternative pathways, it means the universe has been hiding an entire population of impossible black holes right under our noses. These outliers could rewrite our understanding of how the heaviest black holes seed the growth of supermassive monsters at the centers of galaxies. Even more tantalizing is the possibility that GW 190521 might represent a missing link, a middleweight black hole in a mass range we've struggled to observe, bridging the gap between stellar mass black holes and their supermassive cousins. What makes this discovery so thrilling isn't just the mystery, it's the timing. Gravitational wave astronomy is still in its infancy, and already it's revealing phenomena that challenge decades of astrophysical theory. Every new detection peels back another layer of the universe's hidden mechanics, showing us that black holes don't just come in textbook varieties. They're rebels, shape-shifters, and occasionally rule breakers. And as our detectors grow more sensitive, who knows what other impossibilities we'll find lurking in the echoes of colliding space-time. One thing's certain, the universe's playbook just got a lot more interesting. The moon has always been Earth's silent companion, a familiar presence in the night sky. But look closer, and you'll find it's hiding strange, almost artistic swirls, bright, looping patterns etched across its dusty surface like cosmic fingerprints. These lunar swirls, some stretching hundreds of kilometers, aren't just random markings. They're one of the solar system's most persistent puzzles, defying explanation for decades. What makes them even more perplexing is how they resist the moon's otherwise uniform weathering. While most lunar terrain darkens over time under the relentless bombardment of solar radiation, these swirls stay strikingly bright, as if something invisible is shielding them from the ravages of space. Scientists first noticed these enigmatic features in the early days of lunar exploration, but even with modern satellites and high-resolution imaging, their origin remains hotly debated. One leading theory points to magnetism specifically, localized magnetic fields embedded in the moon's crust. Data from NASA's Lunar Prospector mission revealed that many swirls overlap with patches of unusually strong magnetism, suggesting these fields might deflect solar wind particles, preventing the surface from darkening. But here's the catch: the moon doesn't have a global magnetic field like Earth's. So how did these isolated pockets form? Some researchers propose they're relics of ancient asteroid impacts, which could have vaporized iron-rich minerals in the lunar soil, leaving behind magnetized traces as they cooled. Others speculate they might be tied to lava flows from the moon's volcanic past, with magnetic minerals crystallizing in swirling patterns as the molten rock solidified. Then there's the wild-card hypothesis: comet strikes. When a comet grazes the moon's surface, its thin atmosphere could interact with the lunar soil in ways we don't fully understand, perhaps creating temporary magnetic fields or disturbing the surface in a way that leaves these luminous swirls behind. It's a compelling idea, but no direct evidence links any known comet impact to the swirls' locations. The lack of a smoking gun keeps the debate alive, with each new lunar mission adding fresh data and fresh contradictions. What makes these swirls so fascinating isn't just their mystery, it's what they reveal about the moon's hidden complexity. For centuries, we've thought of it as a dead, unchanging world, but these features suggest it's far more dynamic than we imagined. They also raise tantalizing questions for future exploration. Could these magnetic anomalies affect lunar habitats or equipment? Might they hint at untapped resources buried beneath the surface? Every unanswered question is a reminder that even the most familiar celestial bodies can surprise us, offering up secrets that challenge our assumptions and push the boundaries of discovery. The moon's swirls are more than just pretty patterns. They're a testament to the solar system's endless capacity to confound and amaze. And as we gear up for a new era of lunar missions, one thing's certain: the closer we look, the stranger our nearest neighbor becomes. We think we've mapped the universe's contents, stars, galaxies, planets, but there's a glaring hole in our cosmic inventory. Roughly 1/3 of all normal matter, the atoms that make up everything we can see and touch, has gone missing. This isn't dark matter or some exotic substance. It's the same protons and neutrons that build planets and people. Yet for decades, astronomers tallied up all the visible matter in galaxies, clusters, and gas clouds, and the numbers never added up. Where did it all go? The answer might lie in the most overlooked corners of the cosmos. The faint, superheated threads of gas stretching between galaxies like a ghostly spiderweb. These filaments, part of the cosmic web's architecture, are so diffuse they're nearly invisible. The gas within them isn't just hot, it's scorching, reaching temperatures of millions of degrees, which makes it emit X-rays too faint for most telescopes to detect. For years, this meant the missing matter slipped through our observational nets. But in 2017, a breakthrough study used a clever trick. Instead of hunting the filaments directly, researchers tracked how they distorted the light of distant quasars, much like heat haze warps the view on a summer road. The distortions revealed the filaments' presence, and when they calculated the density, something clicked. This faint, intergalactic plasma could account for the universe's missing baryons, closing one of cosmology's most persistent gaps. Yet the mystery isn't fully solved. While these filaments explain much of the discrepancy, some matter might still lurk in even harder-to-spot forms, perhaps as ultra-diffuse clouds in galactic halos or as rogue atoms drifting in the voids between galaxy clusters. The challenge is that the universe is vast, and matter, when spread thinly enough, becomes nearly undetectable with current technology. New X-ray observatories, like the upcoming Athena mission, aim to map these faint structures in unprecedented detail, offering a clearer picture of where the cosmos hides its secrets. What makes this discovery so humbling is what it says about our place in the universe. We've built telescopes powerful enough to glimpse the dawn of time, yet we're still piecing together the inventory of our own cosmic neighborhood. It's a reminder that even the ordinary, the stuff we're made of, can evade detection when it's scattered across the void. And if we've overlooked something as fundamental as atoms, what else might be hiding in plain sight, waiting for the right tool, the right idea to bring it into focus? The missing matter isn't just a puzzle, it's a lesson in cosmic humility, showing us that the universe always keeps a few cards close to its chest. Deep in the constellation Leo, a tiny, flickering star holds secrets that threaten to rewrite cosmic history. SDSS J102915+172927 is its unassuming name, but this ancient relic is anything but ordinary. Born when the universe was less than 800 million years old, it's one of the oldest stars ever discovered, a living fossil from an era when galaxies were just beginning to assemble. Yet what makes it truly baffling isn't its age, but its composition. This star is impossibly pristine, lacking the heavy elements that modern astrophysics insists should be present. It's like finding a cave painting executed with colors that hadn't been invented yet. According to everything we know about star formation, SDSS J102915+172927 shouldn't exist. Stars form from collapsing clouds of gas, and the physics of that process requires metals astronomers speak for elements heavier than hydrogen and helium to help the gas cool and condense. Without even trace amounts of carbon or oxygen, these clouds should remain too warm and diffuse to collapse under gravity. Yet this star defies the rules, containing 10,000 times fewer metals than our Sun, and somehow forming anyway. It's as if the universe whispered a loophole in the laws of physics that we're only now beginning to hear. The implications are staggering. If stars could form without metals in the early universe, it means our models of cosmic dawn might be missing a crucial chapter. One radical theory suggests that pristine gas clouds in the infant universe were far denser than today, collapsing under their own weight without needing metals as cooling agents. Another possibility is that this star isn't truly first generation. It might have formed from gas polluted by just a single supernova, a solitary stellar explosion seeding its birth with the barest whisper of heavy elements. But even these explanations strain to account for its extreme purity, leaving astronomers to wonder if we've fundamentally misunderstood how the first stars ignited. What makes this discovery so electrifying isn't just the challenge to theory, it's the window it opens into the universe's earliest epochs. SDSS J102915 plus 172927 is a time capsule, its composition nearly identical to the primordial gas that filled the cosmos after the Big Bang. Studying it is like getting a blood sample from the infant universe, revealing chemical fingerprints of a time before galaxies, before planets, before even the first heavy elements forged in stellar furnaces. And there might be more stars like it hiding in plain sight, overlooked because their light is so faint and their signatures so subtle. The hunt is now on to find others of its kind, each one potentially holding clues to how the first structures in the universe took shape. Future telescopes, like the James Webb Space Telescope, could spot even older, fainter examples, helping us piece together this cosmic origin story. SDSS J102915 plus 172927 isn't just an astronomical curiosity, it's a beacon from the past, illuminating a path to questions we didn't even know to ask. And that's the thrill of discovery. Sometimes, the universe's greatest lessons come from the stars that refuse to follow the rules. The universe is expanding, galaxies drifting apart in the aftermath of the Big Bang, but something strange is happening on the edges of our cosmic map. Hundreds of galaxy clusters, each containing thousands of galaxies, aren't just moving randomly. They're streaming together in the same direction at incredible speeds, as if caught in a cosmic current no one can see. Astronomers call this phenomenon the dark flow, and it's one of the most unsettling discoveries in modern cosmology. Because if these clusters are being pulled towards something beyond the observable universe, it means there's more out there than we ever imagined, structures so vast they tug on entire swaths of spacetime from realms we can't even glimpse. This mysterious motion was first detected in 2008 when scientists studying the cosmic microwave background, the afterglow of the Big Bang, noticed something odd. The light from distant galaxy clusters showed subtle distortions, as if the clusters were all moving in unison toward a point in the sky near the constellations Centaurus and Vela. At first, researchers assumed it was a measurement error. After all, the expansion of the universe should send galaxies scattering in all directions, not drifting together like leaves on a river. But repeated observations confirmed the pattern. Over 1,000 clusters, some billions of light years apart, were caught in this unexplained flow. The implications are staggering. For these clusters to move in sync, whatever's pulling them must be incomprehensibly massive, perhaps a superstructure lurking just beyond our cosmic horizon. A region so distant its light hasn't had time to reach us in the universe's 13.8 billion-year lifespan. One theory suggests it could be the gravitational pull of another universe, a neighbor in the multiverse exerting influence on our own. Others propose it might be a relic of the chaotic conditions before the Big Bang, a cosmic fingerprint of something primordial and unimaginably vast. But here's the catch: the dark flow shouldn't exist according to standard cosmology. The observable universe is supposed to be mostly uniform at large scales, with no preferred direction or overarching imbalance. This coordinated motion throws a wrench into that assumption, hinting that our patch of the cosmos might be just a small corner of something far grander. It's like standing in a valley and feeling a steady wind, only to realize the breeze isn't coming from anywhere nearby. It's being pulled by a mountain range so distant you can't even see it. Skeptics argue the dark flow could be an illusion, a statistical fluke, or an artifact of how we measure cosmic velocities. Yet the data persists, and with each new study, the mystery deepens. Future telescopes, like the European Space Agency's Euclid mission, could settle the debate by mapping galaxy motions with unprecedented precision. If the flow is real, it would force us to rewrite our understanding of the universe's structure and its ultimate scale. What makes the dark flow so thrilling isn't just the scientific challenge, it's the audacious possibility it represents. For centuries, we've assumed the cosmos ends where our telescopes can't see. But what if it doesn't? What if the universe stretches far beyond our observable bubble, filled with structures and forces we've only begun to sense indirectly? The dark flow isn't just a curiosity, it's a whisper from the unknown, a clue that the greatest chapters of cosmic history might still lie just out of reach. Most neutron stars spin fast, some completing dozens of rotations every second, but Pulsar J1748-2446 makes them all look sluggish by comparison. This cosmic speed demon whirls at an astonishing 716 times per second, so rapid its surface moves at nearly a quarter the speed of light. At that rate, the laws of physics say it should have torn itself apart eons ago, flinging stellar material into space like a spinning water balloon bursting at the seams. Yet against all odds, it holds together, defying every expectation about how matter behaves under extreme conditions. This isn't just a record-breaking pulsar. It's a laboratory for testing the universe's most fundamental rules, and it's showing us just how much we still don't understand. What makes this pulsar so baffling isn't just its speed, it's the sheer impossibility of its existence. Neutron stars are already the universe's ultimate pressure cookers, cramming more mass than the sun into a sphere the size of a city. Their gravity is so intense that a sugar cube-sized chunk would weigh as much as a mountain. Conventional models suggest that when these collapsed stars spin beyond about 700 revolutions per second, centrifugal forces should overwhelm gravity, ripping them apart in a catastrophic explosion. Pulsar J1748-2446 dances perilously close to that edge, yet shows no signs of instability. How? One theory points to its bizarre internal structure. At these densities, protons and electrons might merge into a soup of free-floating quarks, creating a bizarre state of matter so dense and slippery it acts like cosmic grease, allowing the star to spin faster without flying apart. Others speculate that its magnetic field, trillions of times stronger than Earth's, could be acting like a cosmic corset, containing the star's furious rotation with invisible bands of energy. Then there's the wild-card explanation. What if our understanding of gravity itself is incomplete? In the extreme environment of a pulsar's core, Einstein's theory of general relativity might need tweaks, with quantum effects or hidden dimensions subtly altering how mass warps spacetime. Pulsar J1748-2446 could be hinting at cracks in our foundational physics, much like Mercury's orbit once revealed flaws in Newtonian mechanics. Every pulse of radiation it emits is a clue, a coded message about the behavior of matter under conditions we can't possibly replicate on Earth. The implications ripple far beyond this one stellar oddity. If neutron stars can spin this fast without disintegrating, it reshapes our models of stellar evolution, supernova, and even the birth of black holes. It also raises tantalizing questions about gravitational waves. Could these ultra-fast pulsars be emitting faint ripples in spacetime, detectable by future observatories? And if there's a hard limit to how fast a neutron star can spin, what happens when something pushes it over the edge? The answers might lie in the star's exotic surroundings. Discovered in a globular cluster packed with ancient stars, Pulsar J1748-2446 AD likely owes its breakneck speed to a cosmic robbery, siphoning gas from a companion star, a process that transfers angular momentum like a cosmic slingshot. Yet even this explanation feels incomplete. Other pulsars in similar environments don't come close to its rotational fury, suggesting there's something uniquely resilient about this star's structure. It's a reminder that the universe doesn't just test the limits of our knowledge, it gleefully smashes through them. As telescopes grow more sensitive, who knows how many more rule-breaking pulsars we'll find. Each one is a challenge, a dare from nature to rethink what we're certain we know. And in that challenge lies the thrill of discovery, because sometimes the most important lessons come from the cosmic outliers that refuse to play by the rules. NGC 2915 looks like a cosmic joke at first glance, a tiny, shapeless blob of stars floating in the void, so unremarkable you'd scroll right past it in a catalogue of galaxies. But point a radio telescope at it and the joke's on us. Suddenly, this so-called blue compact dwarf galaxy reveals a secret, elegant, sweeping spiral arms, invisible to optical telescopes, stretching far beyond its visible core. These phantom limbs, detectable only through the faint whisper of radio waves, shouldn't exist on a galaxy this small and young. Yet there they are, twisting through the darkness like cosmic ink spilled across an unseen canvas, forcing astronomers to confront a glaring question. How does a galaxy this tiny flaunt features usually reserved for grand spirals like Andromeda? The mystery lies in the mismatch. Blue compact dwarfs are typically chaotic, clumpy galaxies, bursting with newborn stars but lacking any organized structure. NGC 2915 fits that bill. Invisible light, a messy nursery of hot, young stars glowing blue. But the radio waves paint a different story, showing cold hydrogen gas arranged in pristine spiral arms, a pattern that demands some unseen force sculpting it. One leading theory points to dark matter. While this galaxy's visible stars are crammed into a tight central region, its dark matter halo, the invisible gravitational scaffold thought to surround all galaxies, might extend much farther, spinning slowly and dragging the gas into those unexpected spiral patterns. It's as if the galaxy's hidden skeleton is puppeteering its visible flesh, shaping it in ways that defy classification. Then there's the wildcard possibility: past encounters. Could NGC 2915 have brushed against another galaxy long ago, a near collision that sent ripples through its gas, leaving behind these ghostly arms? That would explain the structure, but there's no obvious culprit nearby, no neighboring galaxy close enough to have triggered such a disturbance. Unless, of course, the culprit long since moved on, leaving only these faint echoes behind. What makes NGC 2915 so thrilling isn't just the puzzle, it's the precedent. If a tiny galaxy can masquerade as a spiral, what else have we misclassified? Astronomers rely on shape to sort galaxies into neat categories, but this cosmic oddity proves that appearances can deceive. Some of the universe's most intriguing secrets might be hiding in plain sight, visible only when we switch wavelengths or perspectives. Future radio surveys could reveal more of these shape shifters, each one challenging our assumptions about how galaxies form and evolve. Perhaps the most humbling lesson here is how much we still don't see. The universe isn't just what meets the eye or even the telescope. It's a realm where invisible forces sculpt visible beauty, where the faintest signals carry the loudest revelations. NGC 2915's hidden arms aren't just a curiosity. They're a reminder that every time we think we've mapped the cosmos quietly laughs and reveals another layer of the impossible. The night sky is filled with the fading echoes of dying stars, but in 2006, astronomers witnessed something that shouldn't have been possible. SN 2006G wasn't just another supernova, it was a cosmic monster, unleashing a blast of light so intense it outshone entire galaxies. This wasn't just a star's death throes, it was a stellar explosion cranked up to unimaginable extremes, radiating 100 times more energy than a typical supernova and refusing to fade for months. What made this event so baffling wasn't just its brightness. It was the fact that no known stellar death mechanism could explain it. Theories crumbled under scrutiny, leaving scientists staring at data that seemed to rewrite the rules of how stars die. At the heart of the mystery lies the star's sheer size. Most supernovae occur when stars between 8 and 40 solar masses exhaust their fuel and collapse inward. But SN 2006G's progenitor was a behemoth, likely over 100 solar masses, a rarity in the universe. Stars this massive aren't supposed to explode at all. Conventional models predict they should quietly implode into black holes, vanishing without the fireworks of a supernova. Yet here was proof that not only did this star explode, it did so with unprecedented violence. One radical theory suggests it might have undergone a phenomenon called pair instability, where the core becomes so hot it spontaneously converts energy into matter and antimatter particles. This creates a runaway reaction, a thermonuclear bomb so powerful it obliterates the star entirely, leaving no remnant behind. But even that explanation struggles to account for SN 2006G's lingering glow. Most supernovae fade within weeks as their radioactive fuel decays, but this one burned bright for over 200 days, as if something kept reheating its expanding debris. Some researchers speculate the explosion collided with previously ejected material, creating shock waves that pumped energy back into the system. Others propose the star might have been surrounded by dense shells of gas, which absorbed the blast's energy and re-radiated it slowly like a cosmic echo chamber. Then there's the wildest idea of all, that SN 2006G wasn't a supernova at all, but something entirely new, a quark nova, where the collapsing core forms an exotic, ultra-dense quark star, triggering a second explosion that dwarfs the first. What makes this discovery so revolutionary isn't just the cosmic spectacle, it's the questions it forces us to confront. If stars can die in ways we've never imagined, what other cataclysms are lurking in the universe's shadows? Are there even more extreme explosions waiting to be spotted, ones that make SN 2006G look tame by comparison? The implications ripple far beyond a single event. Supernovae seed the cosmos with heavy elements, the building blocks of planets and life. If some stars explode with far more energy than we thought, they might be scattering these elements farther and faster, reshaping our understanding of how the universe chemically evolves. The hunt is now on for more of these impossible supernovae. With next-generation telescopes scanning the skies, astronomers are poised to catch the next record breaker in action, peeling back the layers of these cosmic anomalies. SN 2006G isn't just a footnote in astrophysics, it's a wake-up call, a reminder that even the most violent events in the universe still hold surprises. And with each new discovery, we're not just rewriting the textbooks, we're glimpsing a cosmos far more dynamic, more unpredictable, and more astonishing than we ever dared to dream. The Boomerang Nebula defies every expectation about how space behaves because at a bone-chilling 1 degree above absolute zero, it holds the title of the coldest natural place ever discovered in the universe. That's even colder than the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. Picture a place so frigid it makes the void between galaxies feel warm by comparison, where temperatures hover just a whisper above the theoretical limit of cold itself. And yet, this cosmic deep freeze isn't some quiet, dormant corner of the cosmos. It's the result of a dying star's violent tantrum, a paradox that's forcing scientists to rethink how stellar winds sculpt the universe. What makes the Boomerang Nebula's chill so baffling is the sheer energy involved in creating it. Most planetary nebulae, glowing shells of gas ejected by aging stars, are hot, illuminated by the ultraviolet radiation of their exposed cores. But the Boomerang is different. Its central star, a red giant in its death throes, is expelling gas at a staggering speed of 164 kilometers per second, so fast that the nebula's outer layers have expanded to nearly 2 light-years across. That breakneck expansion is the key to its coldness. As the gas races outward, it behaves like cosmic air rushing from a pressurized can, cooling dramatically as it spreads. It's the same principle that makes aerosol cans feel cold to the touch, but on a scale so vast it's dropped temperatures to near absolute zero. Yet even this explanation leaves gaps. Why is the Boomerang Nebula so much colder than other nebulae with similar outflow speeds? The answer might lie in its unique asymmetry. Unlike the graceful rings of most planetary nebulae, the Boomerang is shaped like, you guessed it, a boomerang with twin lobes of gas jetting in opposite directions. Some researchers suspect its central star is actually a binary system, with 2 stars orbiting each other in a dance that funnels the outflow into those focused, high-speed streams. This could amplify the cooling effect, like a cosmic air conditioner with its settings cranked to maximum. Others propose that dust grains in the nebula are acting as miniature refrigerants, radiating heat away into space with eerie efficiency. The implications stretch far beyond this one frozen enigma. If we've underestimated how efficiently dying stars can cool their surroundings, it could reshape our understanding of how matter cycles through the cosmos. The Boomerang's extreme cold might also make it a natural laboratory for studying quantum effects that only manifest near absolute zero, a place where atoms move sluggishly enough for scientists to observe phenomena impossible to replicate on Earth. And with the James Webb Space Telescope's infrared eyes now trained on it, we might soon uncover even deeper layers of its mystery. What's truly humbling is how this cosmic icebox challenges our assumptions. We often think of space as either scorching hot near stars or passively cold in the void. The Boomerang Nebula proves the universe has more imagination than that, crafting pockets of extreme cold in the unlikeliest of places. It's a reminder that even in death, stars can create wonders not just with light and heat, but with shadows and chill. And as we peer deeper into its frosty embrace, who knows what other impossible extremes we'll find lurking in the cosmic dark. Black holes are supposed to be cosmic anchors, supermassive giants lurking at the centers of galaxies, their gravity holding entire star systems in orbit. But in 2022, astronomers spotted something that shattered that assumption. A rogue black hole, untethered and adrift, moving through the void like a lone wolf in the cosmic wilderness. This wasn't just a curiosity, it was proof that even the universe's most formidable predators can be flung into the abyss, cast out from the very galaxies they once ruled. The discovery hinged on a phenomenon called gravitational microlensing. As the black hole drifted between Earth and a distant star, its immense gravity warped space-time like a lens, bending the star's light and causing a temporary brightening. From that subtle flicker, scientists calculated the intruder's mass, roughly 7 times that of our Sun, and its velocity, a staggering 45 kilometers per second, far faster than any star in our galactic neighborhood. That speed was the smoking gun. A black hole doesn't just wake up and decide to go for a cosmic stroll. Something must have kicked it out with unimaginable force. The leading theory, a violent cosmic breakup. When two galaxies merge, their central black holes eventually spiral together, colliding in a gravitational dance that can fling the loser clear of the system. Imagine a game of cosmic pinball where the flippers are the laws of relativity, and the ball is a black hole hurled into the void. Alternatively, a supernova explosion could have given the black hole a natal kick, a recoil so powerful it escaped its home galaxy entirely. Either scenario paints a universe far more chaotic than we once imagined, where even the mightiest objects aren't immune to exile. What makes this rogue so fascinating isn't just its backstory, it's what it represents. If one wandering black hole exists, there are likely countless others, invisible nomads drifting unseen through the darkness. Some could be primordial, born in the chaos of the early universe before galaxies even formed. Others might be refugees from ancient collisions, their origins lost to time. Their presence raises eerie questions. How many are out there? Could one pass through our solar system undetected? The odds are vanishingly small, but the mere possibility sends shivers down the spine. This discovery also forces us to rethink how galaxies evolve. Black holes aren't just passive occupants, they're active shapers of their environments, influencing star formation and galactic structure. A rogue black hole stripped of its celestial kingdom becomes a wild card. Could it seed new galaxies if it captures enough gas, or does it wander forever, a dark specter of what might have been? With every new observation, we're learning that the universe has a flair for the dramatic, ejecting its titans into the void as if to remind us that nothing, not even a black hole, is truly permanent. The hunt is now on for more of these cosmic renegades. Next-generation telescopes, like the Nancy Grace Roman Space Telescope, could uncover hundreds, each one a clue to the turbulent history of galaxy formation. This lone wanderer isn't just an anomaly, it's a glimpse into the universe's untold stories, where even the darkest, most destructive forces can become unmoored, set adrift in a sea of stars. And in their loneliness, they teach us something profound, that the cosmos is never quite as orderly as we assume, and that sometimes the most revealing discoveries are the ones that slip through the cracks. Quasars are the universe's ultimate powerhouses, supermassive black holes devouring matter so voraciously they outshine entire galaxies. Normally, these cosmic beacons are loners, scattered across the cosmos like distant lighthouses. But in 2007, astronomers stumbled upon something that shouldn't exist. 3 quasars, each blazing with the energy of 1 trillion suns, clustered together in a tight cosmic knot. This wasn't just a rare alignment, it was a statistical impossibility, a celestial trifecta so unlikely it's like finding 3 needles in a haystack that somehow arranged themselves into a perfect triangle. The odds of such a trio forming by chance are astronomically low. Quasars are already rare, active only when supermassive black holes at galactic centers gorge on vast amounts of gas and dust. For 3 to ignite simultaneously in close proximity suggests something extraordinary, perhaps a titanic collision of galaxies, each dragging its own black hole into a gravitational dance so violent it triggered all 3 into frenzied feeding. But even that explanation falls short. Galactic mergers are messy affairs, and the chaos usually disrupts the precise conditions needed to sustain multiple quasars. For all three to remain active, their host galaxies must have been swimming in an unusually rich reservoir of gas, a cosmic buffet so abundant it could fuel all three monsters at once. Then there's the wild card, dark matter. The invisible scaffolding of the universe, dark matter's gravitational pull could have orchestrated this meeting, drawing galaxies together in a way that nudged their black holes into simultaneous activity. Some models suggest that quasars might cluster along dense filaments of dark matter, like fireflies drawn to a wire. If true, this trio could be a signpost pointing to an even larger, unseen structure, a cosmic crossroads where dark matter's influence is strongest. What makes this discovery so revolutionary isn't just the quasars themselves. It's what they reveal about the universe's large-scale structure. Most theories assume quasars are randomly distributed, but this trio hints at hidden patterns, a hidden order in the chaos. Could there be more of these groupings lurking in uncharted regions of the sky? Future surveys, like those planned with the Vera Rubin Observatory, might uncover dozens, each one a clue to the forces shaping the cosmos on the grandest scales. The implications ripple far beyond a single cosmic oddity. If quasars can cluster, it means the universe's most violent events might not be isolated. They could be connected, synchronized by processes we're only beginning to grasp. And that's the thrill of discovery sometimes. The universe's greatest lessons come from the things that shouldn't exist, the outliers that force us to rewrite the rules. This trio isn't just a curiosity, it's a challenge, a dare to look deeper and question what we think we know. Because in the end, the cosmos always has another surprise waiting, just beyond the edge of our understanding. For 13.8 billion years, the universe has been assembling itself from the first particles to galaxies, planets, and life itself. But before any of that could exist, there had to be a starting point, a chemical handshake that began the cosmos's journey from simplicity to complexity. That moment arrived with helium hydride, the universe's very first molecule, and for decades it existed only in theory, until, against all odds, astronomers found it, hiding in plain sight, 1,200 light-years away, in the swirling depths of a planetary nebula called NGC 7027. This discovery wasn't just a scientific milestone, it was a window into the universe's infancy. Picture the cosmos just 100,000 years after the Big Bang, a seething, opaque soup of hydrogen and helium nuclei bathed in relentless radiation. As the universe expanded and cooled, those nuclei finally captured electrons, forming neutral atoms for the first time. But helium, ever the stubborn element, refused to bond easily. Only when it encountered hydrogen ions, protons stripped of their electrons, did it reluctantly form helium hydride, a fragile molecule that existed fleetingly before being torn apart by ultraviolet light. For years, simulations suggested this molecule kick-started cosmic chemistry, but without physical proof, it remained a ghost in the equations. Then, in 2019, the Stratospheric Observatory for Infrared Astronomy, or SOFIA, a telescope mounted inside a modified Boeing 747, spotted helium hydride's fingerprint in NGC 7027. The detection was poetic. The molecule was found in a modern nebula, a place mimicking the conditions of the early universe. Here, ultraviolet radiation from a dying star strips nearby gas down to its barest components, recreating the primordial environment where helium hydride first emerged. It's as if the cosmos preserved a living fossil, a relic of its own birth tucked away in a corner of the Milky Way. What makes this discovery so profound isn't just the confirmation of a theory, it's the chain reaction it represents. Helium hydride paved the way for molecular hydrogen, which cooled the first gas clouds, allowing them to collapse into the universe's earliest stars. Without that first fragile bond, the cosmos might have remained a featureless void, devoid of the structures that eventually gave rise to everything we know. Yet the hunt isn't over. While NGC 7027 provided the smoking gun, astronomers now scour deeper space, searching for helium hydride in even more ancient environments, perhaps near quasars, whose intense radiation replicates the harsh conditions of the universe's dawn. Each detection peels back another layer of cosmic history, revealing how a universe of particles became a universe of possibilities. And in that journey, helium hydride isn't just a molecule, it's the first note in a symphony that's still playing 13.8 billion years later. In June 2018, telescopes around the world caught something erupting in a distant galaxy, a flash of light so intense it outshone its host galaxy by 100 times. Astronomers catalogued it as a 2018 cow, but it quickly earned a catchier nickname, the Cow. At first glance, it seemed like another supernova, the explosive death of a massive star. But within days, it became clear this was no ordinary stellar farewell. The Cow didn't just break the rules, it tore them up and scattered the pieces across the cosmos. What set this explosion apart was its sheer speed. Most supernovae take weeks to reach peak brightness, then fade gradually over months. The Cow blasted to full intensity in barely 2 days, then vanished just as quickly, its light dropping off a cliff after mere weeks. Even stranger were its emissions, unlike any supernova ever recorded. Instead of the expected mix of hydrogen and helium, the Cow's spectrum was dominated by heavy elements like calcium and titanium, glowing fiercely in ultraviolet and X-ray light. It was as if someone had strapped a particle accelerator to a dying star and cranked it to maximum. Theories erupted faster than the event itself. One leading idea suggested the Cow might be the birth cry of a black hole or neutron star, a newborn compact object shredding its surroundings with jets of material moving at near light speed. Imagine a stellar core collapsing not into silence, but into a cosmic fireworks display, its shock waves igniting the surrounding gas like a match tossed into gasoline. Others proposed it was a star being ripped apart by an intermediate mass black hole, a rarity lurking in galactic outskirts suddenly waking to feast. Then came the wild card: what if this wasn't a star's death at all? Some researchers floated the possibility of a tidal disruption event, where a black hole tears apart a passing star. But even that couldn't fully explain the Cow's bizarre energy signature. Its X-ray output flickered erratically, as if powered by some unseen engine deep within the wreckage, pulsing with rhythms no model could predict. The most tantalizing clue lay in the Cow's aftermath. Unlike supernova, which leave behind expanding debris clouds, this event faded too cleanly, too quickly, almost as if something had swallowed the evidence. Radio observations revealed a faint, lingering glow, hinting at ongoing activity hidden beneath the visible chaos. Could there be a central power source still at work, a black hole or magnetar continuing to churn long after the initial explosion? What makes the Cow so revolutionary isn't just the mystery, it's the door it's opened. Since its discovery, astronomers have identified a handful of similar events, dubbing them fast blue optical transients. Each one defies classification, occupying a gray zone between known phenomena. They're teaching us that the universe has more ways to explode than we ever imagined, and that some of its most spectacular performances might be playing out in categories we haven't even defined yet. This isn't just about adding new entries to the cosmic catalog. The Cow forces us to confront how much we still don't know about stellar life cycles, black hole formation, and the extreme physics governing the universe's most violent moments. Every anomalous flash, every inexplicable flicker, is a reminder that the cosmos still holds entire genres of catastrophe we've yet to witness. And with every new telescope trained on the sky, we're not just searching for answers, we're preparing to be surprised. Most stars move through the galaxy at a leisurely pace, drifting like ships on a calm cosmic sea. But then there are the outliers, the celestial speed demons rocketing through space so fast they're destined to escape the Milky Way entirely. Meet S5 HVS1, a hypervelocity star clocked at over 1.7 million miles per hour, streaking outward on a one-way trip into intergalactic space. At that speed, it could cross the distance from Earth to the Moon in just under 15 minutes, a velocity so extreme it defies everything we thought we knew about how stars move. The secret to this star's breakneck pace lies in the heart of our galaxy, where a monster lurks, Sagittarius, a star, the Milky Way's supermassive black hole. Most stars orbiting it follow predictable paths, bound by gravity's unyielding grip. But when a binary star system ventures too close, chaos ensues. The black hole's immense tidal forces can tear the pair apart, capturing one star while slingshotting the other outward at mind-bending speeds. It's a cosmic game of gravitational pinball, where the loser gets devoured and the winner is flung into the void with enough energy to escape the galaxy forever. What makes S5 HVS1 so special isn't just its speed, it's the pristine trail of evidence it left behind. Unlike other hypervelocity candidates, whose origins are murky, this star's trajectory points directly back to the galactic center, a smoking gun linking it to Sagittarius, a star's violent influence. Its composition tells an even deeper story. Spectroscopy reveals it's a young, hot, massive star, exactly the type you'd expect to find near the Milky Way's crowded core, not hurtling alone through the galactic outskirts. The implications ripple far beyond this one stellar runaway. Hypervelocity stars are cosmic messengers, their paths encoding clues about the black hole's feeding habits and the gravitational landscape of the galaxy. Some might even carry planets with them, though any such worlds would be frozen wastelands, ripped from their native solar systems and condemned to an eternal journey through the darkness. Even stranger, a handful of these stars aren't fleeing the galaxy. They're incoming, hurled toward us by distant black holes in other galaxies, a reminder that the universe's violence isn't confined to our own backyard. Yet for all we've learned, mysteries remain. Not every hypervelocity star traces back to the galactic center, suggesting other mechanisms, like supernova explosions or interactions with dense star clusters, might also be launching stellar projectiles. Some could even be intergalactic intruders, flung our way by unseen forces in the cosmic void. With every new discovery, we're piecing together a more dynamic picture of the Milky Way, one where stars aren't just passive inhabitants but active players in a high-stakes gravitational drama. The hunt is now on for more of these stellar fugitives. Next-generation telescopes like the Vera Rubin Observatory could uncover hundreds, each one a clue to the hidden forces shaping our galaxy. S5 HVS1 isn't just an astronomical curiosity, it's a testament to the universe's untamed energy, proof that even the most familiar objects can be transformed into something extraordinary when caught in the crossfire of cosmic giants. And as we watch these stars race toward the unknown, we're reminded that the galaxy isn't just a static backdrop. It's a stage where gravity writes the scripts and stars sometimes make their grand exits. On August 17, 2017, the universe delivered a spectacle unlike any seen before, a collision so violent it sent ripples through space-time itself. Gravitational wave detectors LIGO and Virgo caught the first whispers of this cosmic cataclysm, a signal dubbed GW170817. What followed was nothing short of a scientific gold rush as telescopes across the globe and in space swung into action, capturing the aftermath in every wavelength from gamma rays to radio waves. This wasn't just another celestial event. It was the dawn of multi-messenger astronomy, where gravitational waves and light told the same story in perfect harmony. The source, two neutron stars, each more massive than our Sun but compressed into a sphere no wider than Manhattan, locked in a death spiral. As they circled closer, their immense gravity distorted spacetime, emitting gravitational waves that traveled 130 million light-years to reach Earth. In their final moments, they collided with the energy of 1,000 supernova, forging a kilonova. An explosion so powerful it synthesized heavy elements in quantities never before observed. For the first time, we had proof that cosmic collisions like this were the universe's ultimate alchemists, creating gold, platinum, and other precious metals in a single, dazzling forge. What made this discovery revolutionary wasn't just the confirmation of elemental origins, though that alone rewrote textbooks. It was the way it united disparate fields of astronomy. Gravitational wave data pinpointed the location. Gamma-ray bursts confirmed the merger's relativistic jets. Optical telescopes caught the glowing aftermath, rich with the fingerprints of newly minted elements. Each piece of the puzzle validated theories decades in the making, from Einstein's predictions about spacetime ripples to models of rapid neutron capture, the process behind the heaviest elements in the periodic table. Yet the surprises didn't stop there. The aftermath defied expectations, glowing brighter and longer than most models predicted. Some scientists speculate the collision left behind a hypermassive neutron star, a fleeting object so dense it pushes the limits of quantum physics. Others argue it collapsed almost instantly into a black hole, its birth shrouded in the explosion's brilliance. The debate continues, but one thing's certain. GW170817 revealed neutron star mergers as some of the universe's most creative and destructive events. This collision didn't just make scientific history, it reshaped our understanding of the cosmos's interconnected nature. Before 2017, gravitational waves and light lived in separate realms of study. Now they're partners, offering complementary views of the universe's most extreme phenomena. And with every new multi-messenger event detected, we're not just watching the cosmos, we're learning to listen to it too. The echoes of those two neutron stars remind us that the universe's greatest revelations often come when we're willing to observe it in every possible way. Most galaxies shine with the light of billions of stars, their spiral arms or elliptical halos glowing against the cosmic dark. But J0613 plus 52 plays by different rules. This ghostly structure drifting through the constellation Auriga isn't just dim, it's virtually invisible. No glittering stars trace its outline, no newborn suns blaze within its depths. Instead, this dark galaxy is a cosmic phantom, a sprawling cloud of hydrogen gas and dark matter that somehow never ignited the stellar fires that light up every other known galaxy. It's as if the universe forgot to flip the switch, leaving behind a relic frozen in time from the cosmos's earliest, most mysterious days. What makes J0613 plus 52 so extraordinary isn't just what's missing, it's what's preserved. Discovered by sheer accident in 2016 when astronomers were calibrating radio telescopes, this dark galaxy appears untouched by the usual forces that shape galactic evolution. Its gas hasn't condensed into stars, its structure hasn't been sculpted by supernova or black holes. It's a cosmic time capsule, offering a rare glimpse into what galaxies might have looked like before star formation began. a primordial blueprint of how the universe builds its largest structures. The leading theory suggests dark galaxies like this could be the universe's failed experiments. In the early cosmos, vast clouds of gas collapsed under gravity's pull, but in some cases, the conditions for star formation simply never aligned. Perhaps the gas was too diffuse, too undisturbed by the collisions and mergers that typically trigger stellar birth. Or maybe dark matter's gravitational scaffolding in these regions was too sparse, preventing the gas from clumping tightly enough to ignite. Whatever the reason, J0613 plus 52 represents a road not taken a glimpse into what might have been, had the universe's recipe for galaxies omitted a key ingredient. Yet the mystery runs deeper. How does a galaxy-sized mass of gas remain so pristine over billions of years, in a universe teeming with radiation, supernova shocks, and galactic collisions? Avoiding star formation for so long seems almost impossible. One clue lies in its isolation. Most galaxies live in crowded neighborhoods where gravitational interactions constantly stir the pot. But J0613 plus 52 floats in near total solitude, a cosmic hermit shielded from the chaos that might have otherwise forced it to evolve. Its gas swirls undisturbed, a quiet backwater in an otherwise turbulent universe. The implications are profound. If dark galaxies are more common than we thought, they could solve a long-standing puzzle, the universe's missing baryon problem. Astronomers have struggled to account for all the normal matter predicted to exist, and these invisible gas-rich structures might hide a significant portion. They could also be the hidden cradles of ultra-diffuse galaxies, those faint, star-poor systems that challenge our understanding of galactic formation. What's most thrilling is how J0613 plus 52 forces us to rethink what a galaxy even is. Must it have stars to earn the title, or is the gravitational framework of dark matter and gas enough? As telescopes grow more sensitive, we're likely to find more of these shadowy counterparts, each one a whisper from the universe's youth, a reminder that the cosmos still holds secrets written in darkness rather than light. And in their silence, they speak volumes about how much we have yet to learn. Imagine holding a photograph from the universe's first birthday, a snapshot so ancient it predates stars, galaxies, even atoms themselves. That's the cosmic microwave background, or CMB, the afterglow of the Big Bang still shimmering faintly across the entire sky. Discovered by accident in 1965, this relic radiation has become our most powerful window into the cosmos's infancy, a time capsule from when the universe was just 380,000 years old. But buried within its subtle glow are secrets that threaten to upend our understanding of reality itself. The CMB's most startling feature is its near-perfect uniformity. No matter where you look, its temperature hovers around 2.7 degrees above absolute zero, varying by less than 1 part in 100,000. These tiny fluctuations aren't random noise, they're the fingerprints of quantum ripples stretched to cosmic scales by the universe's explosive expansion. Over billions of years, gravity amplified those minute density variations, sculpting them into the galaxies and galaxy clusters we see today. It's like finding the blueprints for modern cities hidden in the wrinkles of a newborn's hand. Yet for all its predictability, the CMB harbors bizarre anomalies that defy explanation. Take the axis of evil, a controversial pattern where temperature fluctuations appear oddly aligned across vast swaths of the sky, as if the universe has a preferred direction, violating the cosmological principle that no location should be special. Then there's the cold spot, a region unusually devoid of microwave radiation, spanning nearly 1 billion light-years. Some theorists speculate it could be evidence of a collision with another universe during inflation, a bruise left by a cosmic sibling we'll never see. Others argue it's merely a statistical fluke, but the odds of such a feature occurring by chance are less than 1 in 50. Perhaps the most tantalizing clue lies in the CMB's polarization patterns, delicate swirls imprinted by gravitational waves from the universe's first trillionth of a second. In 2014, the BICEP2 team thought they detected these primordial ripples, a smoking gun for cosmic inflation. The theory that the universe underwent exponential expansion moments after the Big Bang. But the signal turned out to be cosmic dust, a reminder of how elusive these truths can be. The hunt continues with next-generation telescopes like the Simons Observatory and Lightbird, poised to scour the CMB for whispers of inflation's energy scales and perhaps signs of new physics altogether. What makes these anomalies so electrifying isn't just their mystery, it's what they imply about the fabric of reality. If the axis of evil is real, it might hint at pre-Big Bang structures or exotic fields that twisted spacetime on cosmic scales. The cold spot could be a portal to multiverse theories, while anomalous polarization might reveal particles heavier than anything our colliders can produce. The CMB isn't just a static relic, it's a dynamic puzzle, its contradictions pointing to gaps in our understanding of dark energy, quantum gravity, and the very nature of time. Every new observation peels back another layer. Recent studies suggest the CMB's fluctuations might not follow the Gaussian randomness predicted by standard inflation, hinting at interactions between unknown forces in the primordial universe. Others have spotted eerie correlations between the CMB and the distribution of galaxies billions of years later, as if the universe's fate was written into its first light. These aren't just academic curiosities, they're clues to the universe's deepest architecture, written in a language we're still learning to decode. The CMB teaches us humility. For all our telescopes and theories, we're still deciphering the universe's opening lines, grappling with a story that began 13.8 billion years ago. Its light has traveled farther than we can fathom, carrying messages from a time before time. And as we stare into its subtle patterns, we're not just reading the past, we're glimpsing the edges of physics itself, where the known universe gives way to something stranger, wilder, and more magnificent than we ever imagined. Dark matter has always been the universe's ultimate ghost story, an invisible presence shaping galaxies, bending light, and outweighing normal matter 5-to-1, yet slipping through our detectors like a whisper in the wind. For decades, scientists have chased its shadow, building exquisitely sensitive experiments deep underground, where they wait for the faintest tick of a particle collision that might betray dark matter's existence. But here's the twist: some experiments claim to have heard that whisper, while others hear only silence. This isn't just a case of mixed signals, it's a cosmic detective story where every clue contradicts the next, forcing us to question whether dark matter is playing by rules we don't yet understand. Take the case of the Dharma/Libra experiment, buried beneath Italy's Gran Sasso mountain. For over 20 years, it's reported an annual flicker in its detector, a rhythmic signal that peaks every June and dips in December. The pattern matches exactly what you'd expect if Earth were plowing through a wind of dark matter particles as it orbits the Sun. It's a compelling claim, one that survived repeated scrutiny. Yet other experiments like Xenon 1T and Lux, designed to catch the same particles, have come up empty. It's as if one group of detectives found footprints in the snow, while another, standing just feet away, sees only untouched powder. This inconsistency has birthed a spectrum of wild theories. Maybe dark matter isn't a single particle but a diverse family, with some members interacting just enough to trigger Dharma detector while others slip past everything else. Or perhaps the signal isn't from dark matter at all, but an unexpected quirk of atomic physics. a subtle interaction between ordinary matter and Earth's own magnetic field. The most radical idea that we're seeing hints of an entirely new force, one that mediates dark matter's interactions in ways our standard model can't yet describe. The stakes couldn't be higher. If dark matter is more complex than we imagined, if it carries hidden charges or clusters in ways that defy our simulations, it could rewrite the rules of galaxy formation and cosmic evolution. Some models even suggest dark matter might have its own dark photons or dark electromagnetism, a shadow version of physics operating parallel to our own. Others propose that what we call dark matter isn't matter at all, but a flaw in our understanding of gravity itself, a tweak to Einstein's equations that renders the missing mass an illusion. Yet the most tantalizing possibility is that we're on the verge of a breakthrough. Next-generation detectors like LZ and Super CDMS are pushing sensitivity to unprecedented levels, while astrophysical observations like gamma-ray excesses from galactic centers offer indirect clues. The inconsistency isn't a failure, it's a signpost pointing toward a deeper truth. Dark matter isn't just hiding, it's challenging us to think bigger, to imagine a universe where the invisible majority operates by rules we've only begun to guess. And when the answer finally comes, it won't just solve a puzzle, it'll redefine our place in the cosmos. From unexplained radio bursts to rogue black holes, these 30 cosmic discoveries prove one thing beyond doubt: the universe thrives on chaos and surprise. Every time we think we've uncovered its rules, it tosses another curveball, shattering our assumptions with phenomena that seem ripped from science fiction. Fast radio bursts scream across the cosmos with no discernible source. Dark energy accelerates the universe's expansion in defiance of gravity, and entire galaxies spin without the dark matter we thought held them together. These aren't just quirks, they're glaring neon signs pointing to gaps in our understanding, reminding us how much we still don't know. What makes these discoveries so exhilarating isn't just their strangeness, it's the way they force us to evolve. Science isn't a static set of facts, it's a living, breathing process of questioning and revision. Take Tabby's star flickering unpredictably like a cosmic Morse code, or Oumuamua, the interstellar visitor that defied classification. These anomalies don't just challenge textbooks, they demand entirely new chapters, pushing us to rethink everything from stellar evolution to the fabric of space-time itself. Even the coldest corners of the cosmos, like the Boomerang Nebula, mock our expectations, proving that extreme physics isn't confined to black holes or supernova. But here's the real wonder: every mystery we solve unveils 10 more. The Hubble Tension's conflicting expansion rates hint at undiscovered physics, while the dark flow's galaxy clusters move in unison toward something beyond our cosmic horizon, as if pulled by invisible hands. And let's not forget rogue planets drifting untethered from stars, or the Great Attractor's gravitational grip warping our galactic neighborhood. Each discovery is a humbling reminder that the universe operates on scales and complexities we're only beginning to fathom. So, which of these revelations stunned you the most? Was it the diamond planet glittering under its star's fury, or the neutron star spinning so fast it defies disintegration? Maybe the cosmic web's dark matter threads, weaving galaxies together like beads on an invisible string. Drop your thoughts in the comments. We're as curious as you are. And if your appetite for cosmic wonder isn't satisfied, hit subscribe for more deep dives into the universe's most baffling secrets. Because one thing's certain, no matter how much we learn, the cosmos will always have another surprise waiting, lurking just beyond the edge of our understanding. After all, the universe isn't just stranger than we think. It's stranger than we can think.